Could I have my slide on? Great. So first, I'd like to thank the organizer for inviting me to give this talk. And I want to tell you about bounds on the Mellin amplitude in the context of conformal field theory. And this is a work in progress with Matthew Doderson. He was a student of Eva Silverstein at Stanford and is currently a postdoc at Kavli IPMU. He told me he's going to be watching this from Tokyo. So hi, Matthew. Can you hear me? OK. So I want to talk about the Mellin representation of conformal field theory amplitude. And this was known from the 70s. But its relation to ADS-CFT correspondence became clearer, first by the work by Gerhard Mach, followed by Joao Penedones, and many others. And let me first define the Mellin amplitude. So you start with a conformal field theory in D dimension, and consider correlation function of CFT on the sphere, D sphere. And then you're going to do this transformation with this set of variables, and this M is the Mellin amplitude. And if you look at this, it looks like it's a Mandelstam variable that satisfies the same property. If you parameterize gamma ij as product of p's, the momentum, satisfying this on-shell condition as if the mass is given by the conformal dimension with momentum conservations, then it satisfies this relation. But there are various kinematic constraints because you are calculating this with this amplitude. And if you count the number of independent variables, independent Mellin variables subject to this constraint, you find that this parameterization works. Jacobian is invertible, provided that these p-bytes are actually momenta in d+1 dimensions. Now, I thought we started with conformal field theory in d dimensions. So what's the momentum in d+1 dimensions doing? Holography. So Penedones, first Mach pointed out that if you write it in this way, this M satisfies property as if it is an S matrix of a certain field theory. And Penedones made that correspondence more precise by conjecturing this relation between the flat space amplitude and Mellin amplitude that goes into here in the context of ADS-CFT correspondence. Namely, if you have ADS-CFT correspondence, then there are indeed some string theory in d+1 dimensional anti-theta space. So that's where d+1 should come from. And then provided that you probe the energy region bigger than ADS scale, then you should have this relation. That was, by the way, this omega and thetas are polar coordinate for these sets of momentum. So omega is the overall scale of the momentum. Okay? And so this is a relation. And so we're going to assume this relation and use that to study the relation between the correlation function of conformal field theory and flat space amplitude are probed in this high energy region. Now, scattering amplitude satisfies various interesting phenomena, such as Gross-Mendel growth in high energy scattering in flat space. The world is supposed to grow when the energy in the fixed angle becomes large compared to string scale. And also, eventually, that you're going to start forming black hole, and that's going to evaporate. How are you going to see that in ADS-CFT correspondence is an interesting question. And this formula gives us a way to probe such procedure. I should point out that this relation is only valid in this energy scale because flat space amplitude doesn't know about the ADS scale. So for example, when the energy becomes too large, Gross-Mendel string worldsheet starts growing bigger than ADS scale. Black hole can become bigger than ADS scale. Then this amplitude won't know about it. So this is so there is some limit of how much you can do about this, and we'll be careful about it. The main question is that what Gross-Mendel and those things mean in the context of dual CFT, and I will try to partially answer these questions. So we can start with some exercises. So since we have this relation between Mellin amplitude and flat space amplitude, and we know something about flat space amplitude, so we can just plug in those formula into this relation and see what you get. So for example, if you have point particle scattering in ADS, and if the amplitude, you just consider three-level Witten diagram, the amplitude will be polynomial in momentum. And if you plug this into here and do the integral, you get the same power. if you are interested in gross Mendel effect, where the energy is bigger than string scale, then string worldsheets start growing. And so you have some function f of theta where amplitude decays exponentially. So this is much softer decay, the much faster decay, softer ultraviolet behavior compared to the particle amplitude. But you still get the power behavior like that. And if you have strong gravity effects such as black hole formation and evaporation, you can estimate the effect like that with different angle dependence, and you get still the power. So you still get the power, and this is interesting, but pay attention to the fact, and this is going to be important, that these power depend on the conformal dimension of the external operator. By the way, this behavior is very similar to the one that found by Polchinski and Strasser in 2001, 2 decades ago. And they use a formula which is very similar to this one, except that they don't have this exponential factor. And that's because we are looking at different kind of configuration of strings in ADS. So let me summarize. So if you plug in known property of flat space amplitude, then you have these power behavior, but exponents are different depending on point particle limit and stringy effect. Interestingly, stringy regime and strong gravity regime scales in the similar way, and I'm going to tell you why, but with different angle dependence. Of course, flat space amplitude doesn't know about ADS, so you want to make sure that this don't conflict with that. So if you have too much energy, the gross Mendel amplitude string worldsheet starts to become bigger than ADS scale. In order to prevent that, we're going to postulate this. You can postulate this relation, where string length is a geometric mean of ADS radius and Planck length, so that this goes over here before gross Mendel worldsheet become bigger than ADS scale. So this is nice, but this is just an exercise. The question is that how do you can probe this type of effect in the original CFT amplitude? What you can do to probe in this area by looking at physical observable, which is a correlation function of CFT. The answer was already given by Juan Maldacena and David Simon-Zaffen and Ziboedov. Excuse me, Sasha, sorry. 4 years ago, 2 of the authors are here, so they can correct me if I'm mistaken. The bulk point singularity. And so let me first explain this. We can do it in any dimension, but let me explain this in the context of ADS3 CFT2 because notations are simpler in lower dimension. So in that case, you consider 4-point correlation function. And then you have 6 gamma functions in the Mellin amplitude, but the kinematics makes 2 of them the same. So you have 3 square of gamma functions, Mellin amplitude and some kinematic factor where Z is an harmonic ratio as usual. And I assume for simplicity that all the deltas are the same. And first, you can ask in which regime large gamma dominates this amplitude, okay? So you are interested in when this amplitude is dominated by large gamma. So we can approximate gamma function by starting formula. And then and also when gamma is large, actually it turns out that everything sum up to exponent. And then angle integral, so you have 2 gammas, so one is overall scale and the other is angle between them. The angle integral can be done by saddle point, and it's actually become function of the harmonic ratio of the 4-point. So you just get this amplitude. We know that this is a power. We learned that this is a power, and this is an exponential. So there is a competition between power and the exponential. And then, provided that this is order 1, then you land on the saddle point where omega is order 1, given by delta. Okay, so that's not very large in general. So in order to make the saddle point very large, where we can probe this area that we are interested in, we need to make this small. But we can make this small when this is going to be 1. So that requires minus of absolute value of z is equal to 1 plus absolute value of 1 minus z. Okay, so we need to solve this equation. The left-hand side is negative, the right-hand side is positive. So how you can solve this relation? Well, you cannot solve this relation in flat space, obviously, but you can solve this if you do analytic continuation to Lorentzian signature space. So you start from 4 point, all are in t equals 0 plane, but you can move this in the time direction where two of them pairs up to go to time direction. And so you start with this point in complex plane, z plane, but then as you go from t equals 0 to t equals pi, the z goes around both 0 and 1, and the z bar goes around 1 only. So what happens is that the minus absolute value of z, which is actually minus square root of zz bar, goes to plus, and which becomes z. And the right-hand side, this goes to the same thing because both z and z bar goes around 1. And then, but z is greater than 1 in the end, so it becomes z minus 1. So z is equal to 1 minus z minus 1. So it solves the relation. And so therefore, what you see is that after analytic continuation, where t is moved from 0 to pi, this actually becomes like that. And when z equals z bar, in the end, the exponent becomes small. So here is a summary of this. In this conformal correlation function in CFT2, the Mellin amplitude near this bulk point singularity looks like that. And in this case, what happens is that there is actually a bulk point in ADS3, which can be connected to 4 point on the boundary by light-like geodesic. And Landau pointed out that when something like that happens in quantum field theory, there can be singularity. And indeed, what happens is that as z goes to z bar, the competition between the power here and the exponential makes it so that saddle point goes very large. And then if you assume that you only have flat space Witten diagram, then it gives you the power singularity, which is a Landau singularity. And you can repeat this exercise in any dimensions. And then what you see is that this type of Landau singularity happens for correlation functions 3, 4 point, 5 point, all the way to d plus 2 point. Whereas in the generic conformal field theory, you'd expect, since this is a conformal field theory in d dimension, you'd expect up to d plus 1 point correlation function. So you don't expect in generic CFT to have bulk point singularity for d plus 2 point function, such as 4 point function in CFT2. But in ADS, if you assume a point particle Witten diagram, then you see bulk point singularity. So the question is that what happens when n equals d plus 2, where you don't expect CFT singularity in generic CFT, whereas bulk Witten diagram gives you singularity? Well, string theory should help us. So stringy effect, so let's look at the stringy effect. So this is a Gross-Mendel formula which gives you Mellin amplitude like this. If you plug this into that, so I told you, remember that I mentioned that you pay attention to the fact that there is a dependence on the conformal dimension. The power, even though these are power behavior, but the power behavior depends on the conformal dimension. And indeed, that's what helps us, because that makes this combined to 1 over omega square. This is integrable. So that means that even if you set z equals z bar, the integral converges, and you don't get singularity. So this is how you resolve the bulk Landau singularity. The Gross-Mendel behavior gives you this power behavior, but it's suppressed by this dependence on the conformal dimension, which makes this amplitude convergent. So in general, you can see that the Landau singularity in d equals 2 and n equals 4 can be resolved if the Mellin amplitude decays faster than omega to the 3 minus 4 delta, so that this integral is convergent without this factor. And this bound should hold for generic conformal field theory. You can see that this kind of behavior is very much reminiscent of some of the ultraviolet scaling property of the flat space S matrix. And indeed, there are relations between them. So if you look at the original Penedone's formula, it looks like that. So that means that omega, if suppose, for example, flat space amplitude decays faster than any power of omega, such as in the case of Gross-Mendel amplitude, then this integral would be convergent without this exponential factor. Then in that case, by simple scaling argument, you can prove this relation, which is stronger, a bit stronger than this relation. So it's interesting that, in fact, provided that with this mild ultraviolet softness, you can satisfy this bound. Okay? We have not been able to figure out exactly how to saturate this, but this is interesting fact. And so this I hope explains the title of my talk, the bound on the Mellin amplitude. This is what we propose, that Mellin amplitude of generic CFT should satisfy this relation. And the violated only in the limit when you take omega first, you take string scale and Planck scale go to 0 first before you take omega to be large. This can be generalized to any dimension by simple scaling argument. So, for example, for general D and D plus 2-point correlation function, the Landau singularity is resolved if and only if Mellin amplitude decays faster than this, so that the similar kind of integral is convergent. And you can show that, this is a general relation in Penedon's relation. And in that case, again, if the flat space amplitude decays faster than any power of omega, the Mellin amplitude should decay, satisfying this bound. How am I doing with time? I think I'm doing very well. So in fact, you can do a little bit better. So in fact, if you substitute this directly into here, so these are two relations we used. In fact, you find this relation, which is actually what you find in equation 5.10 in the paper by Marcena, Simons-Duffy, and Ziboedov. And actually, we have been very careful with the contour of the integral. So in their integral, the contour go from 0 to infinity. And here, the contour goes to minus I infinity to plus I infinity. So when you do this combination, the 0 to I infinity can go from 0 to infinity. And then there is a remaining piece. And the remaining piece happens so that they are actually finite, even if you remove the string scale and Planck scale. So if you are interested in the kind of behavior of what happens when string scale and the Planck scale become large, then you get the formula which coincide with the formula that they have proposed. And in fact, if you plug in gross Mendel amplitude into this, you can actually carry out this amplitude integral explicitly and express everything in terms of confluent hypergeometric function. Now, this looks complicated, but we found this formula really beautiful because I cannot explain it in the remaining 5 minutes. But in fact, this formula very nicely interpolates between the apparent bulk point singular behavior to the smooth ultraviolet behavior, basically cut off by the gross Mendel type behavior for distance shorter than the string scale. Now you can ask, well, what happened to the strong gravity effect? And if you evaluate all these effects, you find that actually so in M theory, you don't have this string effect. But in the case when the theory is embedded in string theory, this effect washes out the stringy effect, a strong gravity effect, for reasons such as this. So if you start with gross Mendel amplitude, you can check to see in which for which omega that this integral is dominated. And this integral is dominated by this regime. And you can evaluate the effect, and you can compare that. You can also calculate the effect by strong gravity effect. And the latter is exponentially smaller than this one. So in the generic situation, the gross Mendel behavior, even in the short z equals z bar, z minus z bar goes to 0 limit, dominates. However, there is one important thing that to pay attention, that is that there is angle dependence here and here. And this is a gross Mendel angle dependence, and there is also a different dependence for the strong gravity effect, and these dependences are different. In the gross Mendel case, it goes like theta square log theta. So when theta is going to small, then actually this frequency becomes large, this energy becomes large. So in the limit of small angle, the collinear limit, the iconal limit, the amplitude can go over to Planck scale. So that means that there is a window where you take the small angle limit, you may be able to start looking at the strong gravity effect. And in fact, in the case of D equals 3, namely, so in the case of D equals 2, you don't have it because you don't have bulk graviton in CFT3. But in CFT4, if you take the collinear limit, you can estimate it, and actually there are two, so gross Mendel f of theta decays faster than this. This is just log. Here is a theta square log theta. So this decays faster. So in this case, actually, the strong gravity effects start dominating in the so there is a crossover between these effects. And this is something I'm currently investigating. And recently, there was actually also a nice paper by Cardona last month. So let me summarize. So in the context of ADS-CFT correspondence, high-energy scattering phenomena can be probed at Landau singularity, where large omega dominate in the Mellin amplitude. And the resolution of the Landau singularity in ADS D+1 with D+2 point amplitude requires this universal bound, and that's the sort of meaning of the title of my talk. And gross Mendel behavior actually satisfies this with margin of 1. And we found this analytic formula. I'm so proud of this formula. Actually, this is done by Matthew, so it's nicely interpreted this behavior to this behavior, and strong gravity effect dominate in collinear effect. So actually, I'm finishing, but I would like to end with one more thing. So we have been doing this Asian Winter School supported by Kavli Foundation. This is our 14th meeting going to be held in Japan, January 2020. And we have an excellent list of speakers. We felt that any future string theorists should know a little bit about machine learning and quantum information. So we also have 4 lectures, each by expert in this area. This is actually a series hosted in turn by these 4 countries in Asia. And so we're going to announce the application very soon. So I'd like to encourage that to apply to it. So Liam McAllister was very worried about the amount of time allocated to him, and he was negotiating time with Igor, so I'm going to give him more time, so I'm finishing 3 minutes before the end. Thank you.
Okay, thank you for a great talk, Hiroshi. I guess David has a question.
So beautiful. I had 2 questions. One, yes. I tried to do this many years ago and didn't push it through, so congratulations. But I was trying to understand. So if you take string theory, you end up in the classical approximation with e to the minus energy squared, which you used.
So you are talking about this type of behavior?
So, but let's say we put a general power there, omega to the p.
Yeah, so you can have any power here, you still get the same behavior.
Yeah, right. So you, as you know, and you and Paul tried to sum the divergent series, and typically when you do that with n factorials, that gets reduced to omega, to the first power. Which is,
it still gives a behavior.
Yeah, I understand. So, but what in the CFT depends on that power? Actually, so what I was hoping to get when I unsuccessfully looked at this correspondence was a bound on P.
Yeah, good. So I don't have a perfect answer to this, but this power of F, of course, depends on the power of omega for a trivial reason. And as far as we can see, for example, this strong gravity effect, let's see, where do I put it? I must have put it somewhere. Oops, it stopped working. I'm sorry. It is frozen. Okay, so I was about to show the strong gravity effect amplitude. That had a different exponent. Yeah. And, but we didn't quite see the physical difference because as far as this integral is convergent, you get the same power behavior for energy. So,
yeah, okay. Second question was, so you use holography and perturbative high energy behavior to learn about large frequency behavior of the Mellin amplitudes.
Right.
So that's using string theory to learn about CFT.
Right.
But what is it in CFT that requires power behavior for large omega? Are there bounds, unitarity, something?
Right, yeah, so, well, as I said, if you don't I expect this Landau singularity, you get many amplitude bounded by power, certain power. And yeah, so I think that's, so far that's as much as I can say. It could be related to some more general consideration of unitarity and bootstrap and crossing relations. That would be interesting. Yeah, we have been thinking about this. Thank you for asking.
Okay, more questions, comments? Yeah, there is.
I'm sorry, but maybe this
Where is that? Oh, okay, there.
Hi.
Okay.
Maybe I missed this, but the exponential in Gross-Mendel, that depends on the loop.
Oh, this is tree-level Gross-Mendel.
It's tree-level.
Yeah, and so that was what David was asking about.
Exactly.
So I following up with Gross-Mendel, Paul Mendel, and I did recent mention of the amplitude that gave a different power in the exponent.
Okay.
Yeah.
So no.
But for each loop order, you get the same omega exponential omega square behavior. But that is more and more suppressed for higher genus. It's suppressed by 1 over genus kind of things. So if you resum that, exponential of omega square turns into exponential of omega. But it still has the same sort of power behavior for Mellin amplitude.
Sasha?
So in 2 dimensions, you used the fact that in the CFT, the bulk point limit should be regular, right? But in principle, you have more than that. You can bound the correlation function by the Euclidean correlator. And so it's not only bounded, but you can put probably some bounds on the value. And so
so you can say that there could be even stronger bound.
Right. So my question is, can you use this Euclidean correlator to put even stronger bound and say something?
Well,
yeah.
we certainly haven't thought about it, but we should think about it. We're going to do it right after this talk. Matthew, did you hear that?
Okay. No more? Okay, let's thank Hiroshi again for a great talk.